Well, hello, folks. Very good to see you again for part two of these sessions, thinking about laying the right foundations in year 12. As I said at the start, starting on the title slide, starting as they need to go on. Get your year 12s thinking about the right things, the right way, the right ideas, so that they're well set up for success in year 12, but of course, crucially, success in year 13. Last time we thought about sort of algebraic skills. This time we're going to focus on graph skills and obviously clearly there's a massive overlap between graph skills and algebraic skills, and in a sense separating them was a slightly unusual thing to do, but we're going to focus a lot on graphs today. Very much as last time, those are my objectives. I'm going to suggest some topics, I'm going to suggest some examples, and I hope I'm going to suggest the rationale. Basically, why did I choose the examples that I chose? Why did I write the questions that I wrote? Why do I approach these topics in the way that I approach them? So that you can start thinking about what that sort of core idea in graphs curriculum thread should look like. It's a very similar slide to the one I used last time, but it's slightly different. So last time I talked a bit more about a development program, imagining you've got year 12s joining you whose algebra skills are not quite as strong as you want them to be, and not quite on the spot that you want them to be, and you think you feel that you need a sort of a development, a booster program maybe, or just a consolidation program. You've got students coming in with kind of grade 7, grade 8, but maybe you discover they're not quite as fluent as perhaps they would have been in normal times had they had a good boot camp in the run up to GCSE, say. So last time we were so much thinking about a development program. I think this is slightly different. I think quite a lot of the ideas we're going to talk about today are new ideas, not all of them, but certainly quite a lot of them are new ideas. And therefore it's not really about developing something. It's about actually teaching, conveying, and getting that thread across year 12 so that they have got the firm foundation, secure footing. You know, choose your cliche, moving on into year 13. As I said last time for the national curriculum, there are sort of 3 key aspects of the national curriculum. All students must reason mathematically, all the time. Reasoning is like vegetables, little and often is by far the best. They must become fluent, and with my emphasis, a way of developing fluency is through varied and frequent practice with increasingly complex problems. And so all the time thinking about that increasing complexity of the problems. How, as we go from question 1 to question 2, or even from question A, question B, question C, within question 1 and then ABC within question 2, how is the complexity increasing? And then they must solve problems, some of which are familiar and some of which are not familiar, routine and non-routine. And part of the consequence of doing so is that they develop that habit of mind of resilience and perseverance and persistence in seeking solutions. On a very sort of practical level, you know the new A level contains lots of 8, 9, 10 mark questions. You need to persevere to get all 10 of those marks. So whereas perhaps in the past there might have been only 1, 2 large mark questions and lots of structured questions, now the balance is very definitely shifting. So there are far more chunky questions and therefore far fewer structured questions. Those of you who teach the higher attainers, perhaps aiming for university mathematics, they might do the TAMUA test for university applications, or the MAT test for Oxford, or the STEP papers for Cambridge. All of those require students to work through from the beginning to the end, pretty much unstructured, pretty much without scaffolding. And so that persistence, that resilience starts now in year 12. You can't give high attainers the habits of mind they need to solve, say, a STEP question in May of year 13. It begins in September of year 12. So in terms of focusing then, what are the routine and non-routine examples and topics I want to share with you? Well, as you'll have seen from the preliminary questions, kind of the warm-up questions I sent around, and thank you, Emma, for circulating those. I think about completing the square, think about sketching, think about intersecting, think about inequalities. And I put a bit about transformations in. I didn't put that on the warm-up sheet simply because I thought it was long enough already. But I want to say something about transformations of graphs. And fingers crossed we've got time. I've got some lovely stuff with circles I just want to mention towards the end. Thank you very much for your feedback from last time. If you weren't able to do it then, it'd be great if you could do it this time. There'll be a link at the end for doing so. It'd be really useful to look at it, and I hope I've taken on board some of the comments that you've given me. I've not worked with, I'm not sure I've worked with any of you before, actually. I don't. If I have, and I've done a 3-hour session with you before, and you've really neglected, I do apologise for forgetting you. But because I don't know you, it's been really useful to kind of get back from you kind of what worked well, what worked less well. So thank you very much. I've tried to adapt this session in the light of that, and in particular, I've put more questions into this session, but I'm expecting there to be more for you to do as follow-up. So obviously you'll get the slides, and I'm not going to go through anything like all the questions on the slides. I'm going to try and talk a bit more about the rationale behind the questions, why I chose the questions, what I'm trying to draw out through the questions. Partly because I think that's more interesting for you, but also because actually, quite a lot of the procedure activity for these questions is fairly straightforward. Sketching a cubic, it's got stages to it, but each stage is relatively straightforward. The key is to choose the interesting cubics, the cubics which are worth sketching, and so that's what I'm going to try and talk about. So, so therefore, there will be quite a lot of slides where I'll say, look, here's some questions which I think it'd be well worth you're following through later. And I hope therefore that gives us a bit more time for discussion towards the end, but also the chat. Please carry on using the chat lots. You used it quite a lot last time. You could use it. Let's try and use it even more this time, so I can sort of share your thoughts, and I can hear what your responses are to the questions. Like last time, I'm going to start with my conclusion. And the conclusion is the same. I think ideas at GCSE are not often sort of finished off. We have this unfinished business from GCSE. I think inequalities is a really good example of that, and that can lead into trouble in the sixth form. And so recognizing what they know and what they understand from GCSE, and what the misconceptions they might have, or what the limitations they might have, and tackling those. As always with problem solving, there's a specific strategy for a specific question, and there's a general tactic for a type of question. So in developing the students' realization that there are both of those, and also their awareness that when they're solving a problem, are they doing a specific problem, or are they applying a general tactic to a specific problem? Difficulty and struggle, making it hard enough so that they learn. I know the brain is not a muscle. I like the metaphor of the brain being muscle, and people always look horrified that I think the brain is a muscle. My grasp of biology is not good, but it's slightly better than that. So I know the brain is not a muscle, but no sweat, no learning, no pain, no gain. And in terms of getting the maths from them, I'll recap my favorite questions for doing so at the end. And then you may remember this idea from Richard Skemp, and it links in with Vygotsky's idea of the zone of proximal development. This idea, Skemp's idea that to learn new things, we either fit them into our sort of worldview, we assimilate them, we draw them into our understanding, or we sort of enlarge, we increase, we enhance our understanding to accommodate the new ideas. And if you look back at the slides in the previous session and listen to the recording, you'll see a bit more discussion around that. I'd summarize, though, all of those as graphs are representations of functions. So that's what I think to keep thinking about throughout. Graphs as being representations of function. Now, that's not the only thing a graph is, I do realize that. But my approach to graphs is to talk about functions and talk about the graph being the representation of a function. So right from the start, I'm going to use functional notation. I'm going to use mapping notation, x maps to. I could use f of x equals, but again, I find that causes some confusion, partly because there is some unfinished business from GCSE. So I would say that the recurring kind of message for today is to develop in your own teaching the language of graphs as being representations of functions. Actually, to start with functions, and from functions go to graphs, not the other way around. I think that's a really good example of what Skemp was saying about accommodation, not assimilation. We're going to increase our understanding to accommodate the idea that graphs are representations of functions. So straight away then, completing the square. So I'm not asking you for the vertex on these quadratic graphs, I'm asking you for the minimum value of these functions. So what happens then with the students is that they'd come from GCSE where the question always was, what's the minimum value? And so that, let's assume they're okay at completing the square. So they write, this is x subtract 4 squared subtract 18. And then they tell you the answer is 4 negative 18. Now, straight away that tells you either they haven't read the question or they don't understand the question, because they've given you two answers, 4 and negative 18. Which of those is the minimum value of the function? It's the question to ask them to draw out, and make sure they can tell you that, oh, okay, so x represents the input value. So the input that the 4 is being inputted into the function, and then the output, what comes out of the function, is negative 18. And so the value of the function is negative 18. So the minimum, the value is the second number they've written, and they didn't need to write the first number. So hopefully on the next question, they won't do so. And then straight away, you can see how I'm introducing the desirable difficulty, the productive struggle, by not dwelling too long. Now, obviously, in a class, I'd probably do a few more quadratics, but not many, because the risk is that they've learned a procedure, they've learned a rule that what you do is you write that number and you write that number, but one of them you change the sign of. If all they ever do is quadratics, then all they're ever going to learn is you write the number inside the bracket and the number outside the bracket, and one of them, which one, number inside the bracket? Yeah, 50-50, number inside the bracket, you change the sign of. They're going to learn a process rather than necessarily to demonstrate that conceptual understanding. So pretty quickly, you want the desirable difficulty of, say, the quartics. And first of all, there is just making sure they realize that it still works in the same way. So we've got x squared, subtract 4. Now all squared, again, subtract 18. And then we've got x squared plus 4 all squared, subtract 18. And then we've got x cubed plus 4 all squared, subtract 18. And then now I wrote this as sine squared. I wrote this as sine squared x just because that's what we're familiar with. I must admit, early in year 12, I would write it as sine x in brackets all squared. I just write it like that. I don't want them to get confused by the sine squared notation outside the trigonometric identities and equations context. So I would write it as sine x all squared. And so I'm going to write sine x plus 4 all squared, subtract 18. So they do that work, and then, hey, guess what I ask? I ask what's the same, what's different? So over to you. Do you want to tell me in the chat? What are your thoughts about what's the same, what's different? Why these 4 quadratic, I suppose 5 in total, why these quadratic expressions? I mean, you can give me some answers if you want. I suppose I should label them really A, B, C, D, E, shouldn't I? So just, do you want to share some thoughts? What's the point about these examples, or what's a point about it? Thank you. Bearing in mind that sine x has got a restricted range. So if I ask for the minimum value of each of these, perhaps Gary, could you unpack that slightly? I mean, by all means, folks, just tell me some answers. You know, so you got those 4. What are the minimum of each? What is the minimum of each? Ah, right. Thanks, Gary. Yes. So we can't make sine x plus 4 equals 0. So it's not as straightforward. So the answer is not -4, -18. So what can we do? Okay, and I think Stathios, you were getting at the same thing as well. So what could we do, folks, instead? Suggestions then, please. Yeah, interesting. Yes. So when we come to think about this graphically, and we could do that in a moment. We looking to see what the connection is between all of these graphs. You don't have to fixate on the last one. They're the 3 before. Any suggestions for the three before? What's the minimum value? Do any of them have minimum value -18? I mean, they all end -18. Subtract 18. Is that the minimum value for any of them? If it's easier to unmute yourself, by all means do. I mean, I realize typing in the chat is a bit faffy. And the third example is a similar issue. Yes. So thank you, Gary. Gary is drawing attention to the third and the fifth, which is that sine x plus 4 can't be 0, and nor can x squared plus 4 be 0. So we can't make the bracket 0, and therefore we can't get -18 as the output. Question is, okay, so it's not -18. The question is, what is it? So the third one is -2. Thank you, Estathios. Okay, so the third, I think I'm going to go with that. I think the third one is -2. Can I put you on the spot and ask you why you think that? So why is the third one -2? Right. so the first two terms are not negative. So x squared plus 4. Yes, thank you, Leah and sorry, Leah and Reach. No, Reach is your school name rather than your colleague's name. Yes, thank you, Leah. Thank you, Estathios. Sorry, just someone enter the waiting room. Just let that in. So in that third example, x squared plus 4 is always positive. Okay, so x squared plus 4. Okay, yes, I see, Leah and Ketem. Yes, you're right. So x equals 0 gives -2. Yes, and so because that's always positive and that's always positive, then the -2 is going to be minimum value. I was looking at the completed the square form. So my reasoning, I was going with Gary's reasoning. I was thinking that x squared plus 4, what I put there in a red box, x squared plus 4, that is the least that can be is 0. The least that expression can take is 0. So 0. The least that can take is 4. Sorry, the least x can take. So the least that can take is 4. Okay, I don't know why I said 0 there. Sorry. So 4 squared is 16, and 16 take away 18 is -2. Yeah, thank you, Akib. X squared min value is 0, 0 plus 4 is 4, and 4 squared is 16, take away 18 is -2. Whereas the one above is fine, because that can equal 0 when x equals 2. So that's okay. So when x equals 2, what I've just put there in a sort of bluish box can equal 0 when x equals 2, and so we do get -18 as the minimum value there. For the cubic, can the cubic expression equal 0? Can that equal 0? Yes, with the cube root of -4. So that's fine. That's okay with the cube root of -4. That's okay. And so again, I can make the bracket 0, so I can get 0 squared, and so I can end up with a minimum value of -18. Any thoughts for the last one? Any thoughts for the last one? What is the minimum value for the last one? Yes, Gary, exactly. It's as though you read my next slide, Gary. That's exactly my next slide about the graph sketching. Thank you, but that's spot on. So this, yeah, so Gary is saying that this minimum happens twice at when x is +2 and when x is -2. And the last one. I think I can do a little bit better than that. Yeah, constants. So I was thinking -9 also constants. Thank you, because I'm thinking that the minimum value of that is 3. The minimum value of sin x plus 4 is 3, and then 3 squared take away 18 is -9. Okay, so look, I think there's a real example of, for your students, some productive struggle. They can't just use a rule, oh, it's the number in the bracket and the number outside the bracket. They've got to think through actually what's going on with the squaring. And then exactly, of course, this leads into graph sketching. So as Gary sort of suggested. So, so for the first one, we know it's x subtract 4 squared subtract 18. And so, we have obviously in class do a bit more detail, but we know the y-intercept and we know the vertex. And then this one is x squared subtract 4 subtract 18, sorry, and x squared plus 4 all squared subtract 18. And so, as Gary said, this one has the minimum twice because both x is 2 and x is -2, whereas this one has not right to say it's got 2 vertices, but it's got two minimum points. Whereas this one has a minimum point, but it occurs only at x equals 0. The minimum of this expression x squared plus 4 is when x is 0. So the minimum of the whole expression must be when x is 0. And then of course you can think about the roots. You can think about solving this as well and thinking about what happens. And this is okay in both cases because we have so we go about solving it and working out the x-intercepts, and of course we've got some y. Where are y-intercepts? Sorry, I just realized I put that in the wrong place. That should be it, -2, sorry. And we've got some y-intercepts which are indeed out -2, and then we can think about solving it, and so we're going to get you complete the square and solve it, and so we are going to get some crossing points. And the question is how many crossing points. So that's got intercept there, and we'll have some crossing points, and worth checking why they're 2 crossing points. And so that's going to give us sort of the double U for that, and a shape looking like that, which looks like a quadratic, looks like a parabola, but isn't. Now, I'm slightly sort of almost stammering about the graph sketching, because the thing I really want to say is Desmos. I think it's really good to use Desmos. Sometimes to use Desmos first to draw the graph and then explain the features. Sometimes to sketch and then check on Desmos. So I think when I first started teaching, I was very much using graph sketching programs as a check. I've kind of moved away from that a bit, or I've added to that. I often now say sketch on Desmos and tell me what you see. So actually, I'd be perfectly happy with this activity to go, right, let's plot these both on Desmos. What's the same, what's different, and why? So sometimes I want them to sketch and then check with Desmos, or equivalent. I just find Desmos so easy to use. I mean, I know there's Autograph as well, and other products are available, but I find Desmos very, very, very easy to use. So sometimes I want to sketch and then check on Desmos. Sometimes I want to draw on Desmos first and then discuss the differences, and you can go either way. Little sideline, let me just show you something. You may know it, but I only learned it about 6 months ago, and I'm really excited by it. So I'm just mentioning it to lots of people, and about 2/3 of the people I mention it to don't know it. So I'm going to mention it to you very quickly, and if you know it, feel pleased with yourself, and if you don't know it, you might find it quite useful. It's this idea of finding the vertex. We sort of get quite obsessed by completing the square, but completing the square isn't very nice for, it's fiddly for those, it's fiddly for those. So is there another way of doing it? And I just came across this. I can't remember who showed it to me. I think to be honest, I saw it on the interweb. And the idea is this. So you rewrite this as a partial factorization. X subtract 8 subtract 2, or x 2x subtract 1 subtract 1, or x 3 subtract x plus 3. So right, it's a partial factorization. And then the reasoning goes, quadratic graphs are symmetrical. By the way, brackets, we need to prove that. Let's assume that for the time being. Assuming that quadratic graphs are symmetrical, what this is telling me is that there are 2 places where I can see straight away the function takes the value -2. So I can see straight away that I get a value of -2 when x is 0 and x is 8. Or I get a value of -1. I get a value of -1 when x is 0 or x is 1/2. Or I get a value of 3 when x is 0 or indeed x is 3. So it's looking at the first part, which is not a factorization. Oops. Thanks. Click on the wrong thing, sorry. So looking at the first part, which is not a full factorization, it's a partial factorization. But what that tells us is that the function has the value -2 at x is 0, x is 8, or this function, the second function, has the value -1, x is 0, x is 1/2, or the third function has got value 3 at x is 0, x is 3. Now, assuming that we believe that quadratic graphs are symmetrical, that tells me where the vertex is. That tells me the vertex is at 4. That tells me the vertex is halfway between 0 and 1/2, so at a quarter, and then halfway between 0 and 3 at 1.5, and that was 0 and 8. And so it tells me where the vertex is. It tells me the x coordinate of the vertex immediately without completing the square. And I really like that. I only came across it relatively recently. I mean, I think my reservation about it is it only works for quadratic graphs. So it's a bit of a procedural dead end. It doesn't have any of the richness of completing the square. I can't ask questions like these questions using that method because it relies so heavily on the symmetry of the graph. I suppose if you had other symmetric graphs which you knew were symmetric, you could adapt it. But for quadratics, as an alternative to completing the square, I think it's really good. So there you are. There's something which I've mentioned to some people. They really like it. If you've seen it before, then you're ahead of me. If you don't like it, then it's fine. Just stick with completing the square. But I think I really like the argument of it, though I agree it's quite a specialized argument for quadratics. It's a nice example of a specific strategy rather than a general tactic. sometimes I find that where students get thrown is if they sort of do everything rather than choosing the best thing to do. So I put these questions together, and I shall leave them with you. They're going to make a choice. So the idea is to make a wise choice. And slightly oddly, I'm going to say they can either give me the intercept or they can give me the vertex, depending on which one they feel like, depending on which one seems to them easier. So, i.e., some of these complete the square nicely, some of these factorize nicely. So the third one, for example, I'm not thrilled about completing the square with the 7x. I might try to factorize it. For the second one, that doesn't look to me that's going to factorize with that prime number 7 at the end. So maybe I'll complete the square for that one. And of course, the first one is interesting, as you can see. And so that idea of here are 3 graphs, you tell me what you're going to do, what's the same, what's different about them. And then I did the same thing on the next slide. And actually here, I've deliberately left it in the complete the square form, because sometimes what I find is you give it to them in this format, and yet they still go and expand the brackets. So the answer to these questions, surely none of these are you going to try and find the coordinates of the intercepts. The first thing you're going to do is try and find the coordinate of the vertex. I think that's what's natural about these questions. The way I've written these functions is to think about the vertex. But I bet if you gave some of these to your students, at least some of them would expand the brackets and then try to factorize them. And of course, what's interesting is that because where I've chosen it, so the first one's not going to factorize, the second one will factorize, but not very nicely. I mean, you'd have to have surds to factorize it. And of course, the third one does factorize because it's the difference of 2 squares. Do you remember quite how obsessed I was by the difference of 2 squares last week? So recognizing that this is 3 squared, subtract x plus 3 squared. So it factorizes into 3 plus x plus 3 and 3 subtract x plus 3. Now, do they see that straight away? Probably not, unless you've done the work we talked about last week on looking for the difference of 2 squares, being on the lookout for the difference of 2 squares. That general strategy, sorry, general tactic, look out for the difference of 2 squares. So I put some questions like these on the practice sheet, on the sort of warm-up sheet. I wondered what you thought about them. I wondered, these are different to the ones on the practice sheet, so I'm interested in any answers people have got. So this is the idea of thinking backwards. So if I give you a quadratic graph, your students are probably, with practice, going to be able to give me, say, the x-intercepts and the y-intercepts, or maybe the y-intercepts and the vertex. What about going backwards? What about if we have the x-intercepts and the y-intercepts, or if we have the vertex and the y-intercepts? Can they reconstruct the equation? So that idea, again, where does the desirable difficulty, where does the productive struggle comes from? It comes from working both forwards and backwards. So yeah, I think I'll just give you a few minutes to work through those. I'll share some answers in the chat. Exactly, Gary. Yes, exactly. That is the point. That's where certainly where the struggle comes from. Hopefully, where the productive struggle comes from. Leah, I'm not disagreeing. Which one is that? Which one is that? The first one. Okay, so. And I don't disagree. Do you want to tell me how can you say in the chat or out loud how you did it? How you got there?
Hang on 1 second.
I'm loving the reverb. That's so exciting. It's like you're talking from a cave, from deep underground. Okay, thanks, Leah. Okay. So any other suggestions, folks? Ah, I see, Gary. Yeah. Okay, Leah. Okay. Right. Backtrack. Well, actually, Leah, you didn't even write 16x. You wrote 6x, which I wasn't going to draw any attention to. I was thinking, I really don't think it's 6x. But you meant 16, so you didn't mean 16. You actually meant 10, or negative 10. So in terms of doing the first one, sort of the natural place to start would probably be, well, look, if those are the intercepts, that must be the factorization. Something like that. Exactly, yes. You beat me. Thanks, Leah. So that must be factorization. It's kind of, let's move on. No, because that's got an intercept at -12, not an intercept, sorry, at -6, not an intercept at -12. And so it's going to have to be 2 lots of that. Yes. Okay. and then something similar for the others. So for example, sorry, I've written 4, sorry, that's the wrong way around, isn't it? Sorry. No, sorry, that's I misread my own question. So 4, 0 is the x-intercept, right? Yeah. So x subtract 1. I thought that was the y-intercept. No, the y-intercept is -4. Okay. And so so those are the roots. Is that okay? No, because that's got intercept at +4. So presumably we want the negative of that, the negative, and which constants you've expressed very nicely. Yes, I like the way you've rewritten that as 1 subtract x. And then, of course, the whole point about touching, making sure the students have remembered what touching indicates. So y equals x plus 2 squared. Does that work? No, we need the extra factor of 3. So exactly as you said, Gary, in the chat, the main struggle is working out the coefficient of x squared. I would always start with the factorization. Sometimes students start by trying to guess x squared, basically ax squared plus bx plus c, the coefficients one at a time. No, start with the factorization and then adjust accordingly. Now, of course, they can't do that immediately. They need to play around, either, make some suggestions, try on Desmos, but actually the whole idea of experiencing what the effect of the coefficient, change of the coefficient does, the fact that it stretches parallel to the y-axis, they need to experience that from Desmos or something similar in the first place. So I'm not saying this is not lesson 1, but this idea of thinking backwards. And then, of course, the same thing here with now the vertex. So we sort of think to ourselves, well, I don't, tell me in the chat, anyone fancy telling me the answer of any of these? Using the knowledge of the vertex and the intercept. So share some thoughts. Thank you, Katam. By the way, if I mispronounced your name, I apologise. Sorry. I'm hoping I'm close enough. So Katam is suggesting x plus 3 all squared plus 5. I mean, that certainly fits, doesn't it, with the vertex being at -3, 5.
Yeah.
And does it
Robert,
work?
we are working as a team here, myself and Dr. Duckett here, Terry.
Oh, sorry, I didn't hear that. Sorry.
So we are working as a team, myself and Terry next to me.
Oh, okay, good plan. Working team. Was that Terry? Terry?
Thank you.
But you're a good team, because I agree with your answer. Because does that work? Yes, because 0 plus 3 is 9. Sorry, it's 3, and then 3 squared is 9, and 9 and 5 is 14. So that seems to work for the first one. Okay, then. So we've got these sussed, haven't we? We can do all these really easily. So the next one's going to be x subtract 1 squared subtract 4. But unfortunately, that's not correct, because that's got a y-intercept of what's my y-intercept there? That's got my y-intercept of I've lost train of thought. Have I got that? Yes. So that's got a y-intercept of -3, which is not -2. Okay. So how are we going to correct it? Sorry, I was distracted by the chat. So Constance is suggesting that. Do we agree with that for Constance? Does that work? It would seem to, because when x is equal to 0, we get -1 squared, which is 1, and then times by 2 is 2, and then take away 4 is -2. Why is it not? So what the students will sort of say is nothing about the previous questions. They'll sort of say, well, why is it not x subtract 1 squared subtract 4? And then the reasoning for that is, well, that gives us a vertex, sorry, an intercept of a -3, and I want -2. So why is it not 2/3 of that? Why do we not put a factor in of 2/3? For the second one? So being ready to think through, why is that not the case? So why do we change the coefficient of the square bracket, not the whole expression? Being ready for that answer. And then thank you, Asutta, for the last one. Suggesting y is -2.5, x subtract 2 squared plus 7. It's always nice to have the answer, because then we can check. And so when x is 0, we get 4 times by -2.5, which is -10 plus, and that will give us -3, I think. So I'm not wholly agreeing with you on that one. That will give us -3 as the intercept, not +3. But I mean, thank you for suggesting it. I'd much rather answer in the chat. We can reflect on. So okay, so not -2.5. Happy for anyone to give me a suggestion. But you got the idea. You got the idea. So, and of course, this is what the students need to go through and do. So thank you very much, everyone for suggesting it. And please don't worry about making mistakes. That's what we're here for. Okay, so there you can work on those together, and I hope you can see the value of that thinking backwards. You can do the same thing with straight lines. I tried to make the table in PowerPoint and it was just too fiddly to do so. So I thought I'd just make it in Word and photocopy it. Screenshot it and photograph it. But I can send you the original if you want it. So just again, going backwards, you can see straight away the structure. You can see explicitly the structure. So you've got the equation, and then normally we'd say, well, here's the equation. What's the intercept? What's the gradient? What's the x-intercept? And you can see the two I've suggested. There's a bit of rearranging first. But of course, once I've got two of those, I can work out all the others. And so that idea of kind of working backwards. So, you know, the third one's straightforward. Well, if the gradient's 2 and the intercept is -0, -3, then we kind of know it's y equals 2x subtract 3. But what about that? What about when we have the x-intercept and the gradient? Obviously, we can work it out, but how do we go about doing so? So if you want to kind of enliven y equals mx plus c, something like this is a good way of getting thinking sort of forwards and backwards. The only disadvantage of this table did occur to me after I'd made it and screenshotted it and dropped in the PowerPoint. That the disadvantage of it is that by having a gradient column, I'm requiring to have a gradient answer. And so strictly speaking, it's quite hard to have a vertical line in this. I mean, I suppose I could have had a third or an extra example on the bottom. It can't be stated, it can't be defined. That would have been a bit of a giveaway. So just be slightly careful that in giving values for the gradient, or assuming there are values for the gradient, we are missing out something really important, which are the vertical lines in x equals 3, x equals -2, etc. But just as a model, as a structure for the idea of working forwards and backwards. Here's an equation, you tell me stuff about it. Here's the stuff, what's the equation? That came up, by the way, in the practice. So this was one of the practice questions. And I'm interested to know how people did it, what people's thoughts were. I use this question quite a lot with students, but also with trainee teachers. So when I'm training beginner teachers, sort of NQTs or even PGCE students, they often go straight away to let's make an equation. So sort of the natural thing for a beginner teacher to do is to go, oh right, equation straight line, y equals mx plus c. Or maybe what's obviously better for A level is y subtract 2 is -1/2 of x subtract 5. So that's definitely a better equation to be using in the sixth form. It's just more adaptable later on for year 13. And so therefore something like 2y subtract 4 is -x plus 5. And so 2y is -x plus 9. And then substituting the coordinates in. And so when x is 9, y is 0. And when x is -4, we get 4 and 9 is 13, and so we get y is 6.5. And when y is -2, we get -x plus 9 is -4, and so x is equal to 13. Right, okay, whereas, Simon, that's exactly what I was hoping for. So this to me is what you would call procedural fluency, PF, procedural fluency. It's good, it's fine, it gets the answer. What's much more interesting is what Simon's put in the chat, which develops and exemplifies conceptual understanding of gradient. So we've got the 0.52, we've got gradient of -1/2, so we know we're going downhill. So it's 9. I don't know 0 yet, do I? It's 9 something. And what's happened? We've gone across 4. So to get a gradient of -1/2. We must go down 2, and so we must get to 0. Yes, so 5 to 9 is +4, so I need to subtract 2 from the y coordinate. And that to me is showing a solution such as the one I've sketched on the right. That is showing to be the conceptual understanding of gradient as being the scale factor from the change in x to the change in y, or the ratio of the change in y to the change in x, or indeed just the fraction, change in y over change in x. I mean, the best way of thinking about gradient is the gradient is the change in y for a change of 1 in the x direction. So every change of 1 in the x direction is a change of -0.5 in the y direction. So by scaling up, a change of 4 in the x direction is a change of -2 in the y direction. Exactly. So using the gradient as a scale vector, and of course that sets you up for 3D, because in 3D, vectors 3D in year 13, they've got to move away from the idea of gradient and start thinking about components, about parallel components, or scale factors between the components generating parallel vectors. Sorry, I meant to say. So it'd be interesting to do this with your students, and do they only have a fluency, a find the equation substitute method, or do they have a method which shows their understanding of, as I say, a definition of gradient? It might be the fraction, so -0.5 is going to be the same as what over 4, change in y over change in x. Much better would be a formal definition, which I would say is the value of the gradient is the y change you get for an x change of 1, positive 1, as you move on that line. Again, this is a question I use a lot when I'm asking students, but also again training teachers to work out the area of the triangle. And there's one a bit like it on the practice questions. And so always first thing is draw a picture. So we've got -2, 0, we've got 3, 5, and we've got 4, -2. So that's my triangle. What's its area? Just strategies, I think, folks. I mean, if you're super speedy, you can work out the value of the area. That's fine. But strategies, please. Strategies for working out the area of this triangle. What would you want your students to do? Certainly can move the whole thing along. Yes, that would definitely help. Yeah, I like that, Garrett. Yeah, shift the whole triangle. So one of them is 0, 0. Yep, that's going to make life a bit easier. And then what next? That's a nice idea, Simon. So Simon is suggesting. I mean, I was about to say circumscribe it, but of course it's not a circum. It's square scribe it, and then they've got 3 right-angled triangles. That's by far the best way of doing it, I would say, which is and I'm just going to pick you up, Simon, on something. What am I? I'm going to challenge Simon on something he said. What am I challenging Simon on what he said? Tiny nano challenge for what Simon has said. So I like the strategy. Area of the quadriscribing shape, and then subtract. It's not a square, it's a rectangle, because it's 5 to -2 is 7 and 4 to -2 is 6. So it's a 7 by 6, thank you, Simon, 7 by 6 rectangle, and then we subtract the right-angled triangles. Okay, now all I'll say is I've done this a lot, and very few people suggest that. Most people suggest, well, what a lot of people start doing is start finding equations of lines. It's, what's the equation of that line? What's the equation of that line? Find the perpendicular bisector, and decide the perpendicular height, and then they find the perpendicular, and it just gets really complicated. So the best thing by far is to do what Simon suggested, which is to surround it and chop off. It's basically like being at primary school. How do you cut out a triangle? You get a square of paper or rectangle, and you cut off the corners, and as soon as you give people paper, it becomes really obvious. It's a nice example of where using the concrete, going back to something practical, is really powerful. Sort of halfway house. If you didn't do that, what Simon suggested, if you didn't do the kind of really complicated final equations of all the lines, anything else? Anything about this triangle? Hint, hint. So you work some distances and use half of B sine C. Yep. If you work out the distances, do we notice anything? Hint, 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 hint. If we work out the distances. So if we go with Recker's idea and work out some distances, some side lengths, what do we notice? If I call it ABC, so it might be a right angle triangle, Andrea. It's well worth checking whether it is. Okay, that's nice. Sort of area above and below. Yeah. I think you still have to find that point though, don't you? that's a bit fiddly. I mean, it's nice. I like the idea, but you still have to find that extra point there. Yeah, exactly. Distances AB. Any suggestions for the distances AB and BC in particular? Any thoughts? AB is 5 and BC is root 50. So BC is definitely root 50. I'm absolutely happy with that because it's across 1 down 7. So BC is root 50. I think, Johnny, AB is root 5 as well. Is root 50 because it's across 5 up 5. AB is across 5 up 5. So it's across 5 up 5. So it's 25 and 25. So AB is also root 50. And then AC is across across 6 and down 2. So across 6 down 2. So AC is root 40. AC is root 40. So great question from Andrea. Right angled. Is it right angled? Yes or no? And if it's not right angled, is it anything else? And does that help us? He says, not very subtly, colouring something in pink. It's isosceles. It's an isosceles triangle. It could be right angled. It's not because those three numbers don't obey Pythagoras. 50 plus 50 would have to be 90, and it's not, it's 40. So it could be right angled, but it's not. But it is isosceles, and therefore it's quite easy to work out because it's an isosceles triangle. So an isosceles triangle, we therefore actually know that that's root 50. This is a half of root 40, and so we can work out what the h is, and then we can take it from there. So it's an isosceles triangle. So the height, perpendicular height, bisects the base. Now, obviously, I made this question to draw out these points. A random triangle would not be as nice, but that's the point. It's getting the students. So I'm teaching primary. Probably better not call sixth formers children. Getting the students to think sideways, to take a step back and think of all the different ways they can work out this problem. Yes, there's kind of a brute force coordinate geometry, but there's lots of other ways as well. And I really like giving students one question to work on in 3 or 4 different ways. I much prefer one question answered 3 ways than 3 questions all answered the same way. Okay, so we're going to head on to cubics, and if you're very observant, you'll notice the coffee slide is coming up soon. So what you might want to do, actually, let's take a slightly longer coffee break. Let's take 10 minutes till by the time I finish talking till 3:05. And what I'd like you to do is I'd like to play around on Desmos or something, or whatever you prefer, and sketch those graphs, those cubics, and just think about why I chose them. So what properties do they have? What's the same? What's different? Why did I choose those ones? And imagine doing it in class. Kind of what questioning would you use? What's Desmos? OMG! What's Desmos? Desmos is amazing. I will, in which case I'll do a very quick. So if you know Desmos and want to disappear, that's absolutely fine for 10 minutes. If you don't know Desmos, hang on. I'll do a quick Desmos demo in 2 minutes. I'll take 2 minutes to do a Desmos demo. So why don't, because I can't quickly copy these from the PowerPoint into the chat. So why don't you take a screenshot maybe of these? Or something like that, and then play around with these on Desmos for the next 10 minutes. Let's regather at 3:05. And if you're not sure about Desmos, then just hang on for a moment, and I'll just do a quick. I'll change the screen share, and I'll show you what Desmos looks like. Okay, so play around with those equations for 10 minutes. Plot them on Desmos. Think what's coming out. What are you seeing? Why have I chosen those equations? What do I want the students to be thinking about when they look at those equations? Right, I will stop sharing. And if you're not sure about Desmos, hang on for a minute or 2. So Desmos is a free graph sketching program on the interweb. So if I just get to check what I'm sharing. Yes, okay. So you should be able to see some leaves. Hopefully you can see some leaves. So Desmos, just put it into Google. In fact, that comes automatically. So are you seeing a screen which says "Let's learn together"? Anyone who's still looking at the screen, saying "Let's learn together"? Shashi, I'm assuming you're still there. Yeah, great. Okay. So graphing calculator. Click on that, and then we just start typing. So what did I have? I had y equals, and then x, and then shift 6 to make cubed. and then just kind of I press the arrow key, subtract 2, shift 6 squared, press the arrow key, subtract 11x plus 12, and then I've got the graph of it. Now I can scroll, I can zoom in and out. What you can't do very easily is change the x-axis without changing the y-axis. You have to do that in settings. So what I can do is I can leave the y-axis as it is, but I can change the x-axis, say just to -8, not really -6, say to 6. Okay, and so I can just play around with it and get the x-axis looking a bit better. So just click on the spanner and change the settings. And then I've wanted another one. My next one was y equals x cubed, subtract 14x, subtract 8. And then I've got that one, and we can see something else. I might want to zoom out slightly just so I can see a bit more of the features. And so you just type it, and it changes. You can change the colors if you want. So you click on the wheel. You can then change the color, make it purple if I feel like it. I can make it dashed if I feel like it. It's just very, very straightforward, and it's free, and it's really easy to use. Okay. So let me go back to my PowerPoint. I shall put those slides back up, and you can play around if you wish to. I will just pause the recording though. So just to recap, you think about these graphs, these cubics. What did you notice? Yeah, they've all got the roots the same. They've all got one root, x equals 4, and some of them therefore then have three real roots. Some of them have 3 nice roots. Some of them have 3 real roots too, which are not nice, are surds, and the various kind of combinations that go with that. And of course, when you plot them on Desmos, it's really easy to see they've all got the same root because they all go through the point 4, 0. They all have x-intercept 4, 0. Other thoughts? Particularly for the ones that didn't have 3 real roots. I mean, possibly you quite rightly we're doing the coffee bit rather than the Desmos bit. That's absolutely fine. I'm not going to spoil the surprise, so I'll let you explore these and play around, and you can kind of guess where it's going because these are cubic graphs, and you know that cubic graphs have got varieties of shapes. Some cubic graphs have got 2 turning points. Some cubic graphs have got a horizontal point of inflection. Some cubic graphs have a non-horizontal point of inflection. So obviously that's what these examples are drawing out. But deliberately, as Andrea says, I chose them all to have an intercept in common, so that the students can then think about the effect of the other factor. So they all factorize with x subtract 4. They all have x. They're all the form x subtract 4 something. And the question then is, what does the something do for the other properties for the intercepts and the possibility of turnings? And then those questions as well. Same sort of idea. So there's some algebra here. Time back to last week. So how do we find the coordinates? Well, we make that equal to -8, and then we go about solving that cubic equation, which we talked about last week. Good ways of doing so by factorizing using the grid. And then same thing here. Obviously, make it equal to 2x subtract 8 and equals -x subtract 4. What happens when you do so? Well, again, you get the things that you might expect. So you might get 1 root, you might get 2 roots, you might get 3 roots. Maybe one of these is a tangent. Maybe one of these is a tangent at a point of inflection, etc., etc. So these questions are the value of them lies in the working through them, which I'm not going to do now. You don't want to watch me solve a cubic equation and probably get it wrong. You don't want me to do that. So when you solve them in class, when you solve them with your students, when you solve them by yourselves, it's thinking, okay, what's the algebra telling me? So, for example, this one, the first one, it is the case that you'll get 3 repeated roots. So the algebra is telling me 3 repeated roots. But how can that be? How can a line cross a cubic 3 times in the same place? Well, does it mean it looks like that? Well, that doesn't look very cubic, does it? No. Oh, I see. So that's where the idea of the horizontal point of inflection, the momentarily horizontal point of inflection comes. And then, of course, you get Desmos out. And so you get Desmos out and you play around with the scales so they can see what the graph is doing at the point where the y-coordinate is equal to -8. And then you've got some other ideas to think about here. So yeah, I've chosen these lines deliberately because they will start students thinking about tangents, points of inflection, double roots, triple roots, before they do anything on calculus. They can talk about tangents, they can talk about gradients of curve being defined as the gradient of the tangent to the curve at that point, before they do any work on calculus. Get the ideas up ahead in advance, so that when you come to do the work on calculus, that's not you're not overloading them with the differentiation and the equation of tangent, and also not a problem. Thanks, Katam. Thank you. So you're not overloading them with the differentiation, the algebra, the substitution, the solving, and also the geometry of, well, what's going on with the tangent? Why have I got the same answer twice? So exploring tangents first in advance of using them, say in the context of calculus of differentiation. Okay, inequalities then. So I think inequalities really benefit from the functional way of thinking about graphs. Think about graphs as representations of functions. Because the functional notation, the functional idea really embeds the idea that a range, well, okay, strictly speaking, a domain, but you know, we'll use the word range for the time being, a collection of x values go into the function, and then out come a set of other values, which we can choose if we want to, but we don't have to, as the y values. So this is totally self-defined, self-contained. It's defined perfectly well without any axes. They've got input values, we've got output values. We've got a table of values, I suppose. You can sort of say, you know, we can go back to something very straightforward. We have a table of values. The input values and the output values, you know, input value of 0, output of 6, input of 1, output of 10, input of 2, output of 14, etc. So can we find the value that satisfies, i.e. can we find the input value which gives an output of 11? Yep. We've got the graph because it's asked to sketch it. So we can plot our values. So we've got our input values, we've got our output values. So the y-axis represents our output values. So these are our 4x plus 6 values. These are our x values. And we want 4x plus 6 to equal 11. Well, clearly, therefore, we can just think about solving that. Was it 1 1/4? Yeah, 5 over 4, 1 1/4. And then we can start to think about the range of values that give us the inequality, less than 11, say, or greater than 2, say. And I think because my experience is that by talking about functions, you make it clear right from the start that there are lots of possible values of x going into the expression, generating lots of possible values coming out of the expression, and therefore we want to find lots of values of x, all of which give an output of less than 11. So you're undoing, hopefully, any kind of lingering memory of solving inequalities is like solving equations, but you have to remember there's a funny sign in the middle. I mean, how they've been taught to solve inequalities at GCSE varies considerably, but often can be quite ropey, quite conceptually ropey. So they sometimes sort of say, oh, it's like an equation, but you've got an inequality sign. It's completely different, because for an equation, we are looking for, well, a finite, I mean, in this case, linear 1, but in general, a finite number of x values that make the statement true. Here, we're looking for an infinite number of x values, a range, a set, a domain, a set of x values that make the number true. So it's nothing like an equation. Just because it looks like it doesn't mean conceptually it's anything like an equation. And so you're really trying to stop them thinking it's like an equation. And I find making them think about the graph, making them visualize the representation of the function, and hence visualize the representation of the equation, the single solution that satisfies it, and then the range of solutions that satisfy the inequality. That seems to me to do some way to overcome, to dismantle some of the architecture they might be bringing with them from GCSE. So I think it's really worth making a big fuss about thinking about these expressions and these inequalities in terms of functions, and the same thing here. So we've got here we've got the quadratic function. We've got our input values, we've got our output values, and so we can ask ourselves, when do we get output of 3? That's got some nice answers for that. -1 and -3. And then what values, plural, what set of values, plural, give us those various ranges of output. So outputs which are more than 6, outputs which are less than 11, outputs which are more than 2. And so if they're thinking that I've got my input value x and my output value x squared plus 4x plus 6. So when x is 1, I get a value of 11. So I plot the point 1, 11, and that tells me that when the input is 1, the output is 11. Then the idea of thinking about values of being more, output values being more than 11, and output value being less than 11, start to make a lot more sense, because you're just saying where do I have input values which take me higher up the output axis or lower down the output axis. And so they're not getting confused about where the y values come from and thinking about inputs and outputs. And so I find that very powerful, and I do all my work on inequalities in the language of functions. So something like this, and you might even want to do this first. Actually, this is a bit more straightforward, perhaps. So you've got some two functions that we know. So we've got the function y equals 9. So the output is always 9, and we've got the function y equals x squared, and so the output is always the square of the input. So where do we get the exact solution? Well, obviously there and there, 3 and -3. And then what x values give me outputs more than 9? So how do I see that? Well, this is my output axis, and this is my input axis. So where on my input axis do I go to a level, go to a place on the output axis which is higher than 9? So obviously, if my input's there, I go high. If my input's there, I go high. If my input's there, I go higher. And so my values are x is more than, my inputs are more than 3, or my inputs are less than -3. Oh, sorry, Gary, I missed a question. Yes and no. No, I think yes, but for the right reason. So I think as I would introducing quadratic inequalities to reinforce the functional language, yes. Introducing quadratic inequalities to teach them how to solve quadratic inequalities, no. So I think as a way of approaching it, as a way I'm trying to sketch here, by thinking about in terms of inputs and outputs. So the output happens to be quadratic, the output happens to be linear. As examples of output expressions, and then using those to answer questions, some of which may be inequalities, absolutely. As a topic to teach them how to do inequality questions, no. And so just in terms of the output, and what I find is because there's no y value here, they don't get mixed up with the y values and the x values. They're just going, right, I want the output to be larger than 9. What inputs give me outputs larger than 9? Okay, so output inputs like 4 and 5 and 3.1 and 3.01 and 3.001, etc., etc. And then example questions like that. So what's wrong with that? What's wrong with? Obviously, we know what's wrong with that, but can they tell you what's wrong with that? I mean, first of all, do they challenge it? I mean, is it wrong? And then what's gone wrong? Why is it not correct? Well, because x is bigger than 3, we can bigger than -3. We can see our inputs there. Those are the inputs for x is bigger than -3. And some of them give x squared larger than 9, but not all of them. So it's definitely it's a challenge. And the question is unpacking why that's happened. I've done some more examples on the next 3 slides, so you'll have these to play around with. So it is exactly the same. I have just cut and paste and changed the functions. So same sort of idea. So let's represent the outputs being x squared. Being the input squared, and let's represent the outputs being 3 times the input. And then let's find out where they're mutually satisfied, where we get the same output for the same input. And then where do we get an input of one being larger than input the other? And then what's wrong with that argument? And there's that whole sort of language of talking about what you're saying is I want the output of one of these functions to be equal to the output of the other function, or I want the output of one of the functions to be larger, greater, higher up, given that I'm representing on a vertical axis, to be larger than the output of the other function, and just not having any y values there. I want the y of x squared to be bigger than the y of 3x. Even that's baffling me as I say it. But I'm talking about the output of one function compared to the output of another function, and they're either equal or they're not. And if they're not equal, one of them is larger than the other. So I found that very powerful. And the example there with reciprocals, and there's an example there. Slightly more subtly, this one actually. So you might want to think the fallacies of the previous three are not the same problem here, are not the cause of the issue here. So the fallacy here is about the square rooting, and the fallacy here is about dividing by x. There is an issue with this one. Or maybe hopefully your students will recognise this should be a challenge, not an agree. Hopefully your students will tell you that, and they'll be able to unpack why that's the case. In terms of the sketching, and then obviously, I've chosen quite simple functions because these ought to be easy for the students to sketch. Not necessarily at the beginning of the course, but pretty soon. If they've got to the end of November and they can't sketch 0.5x cubed, then obviously there's a little bit of a concern going forwards. So the focus is not on the complexity of the graph, the focus is on the reasoning about comparing the two representations and what they are saying. They are saying that how far up you are on the representation, it measures the size of the output, the magnitude, the value of the output corresponding to that given input. So then transforming graphs, transformations of graphs. Now, obviously, this is not lesson one, so I'm assuming you would do some fairly standard work beforehand, getting to understand what the transformations are. And this is where Desmos is brilliant, because you just draw a graph on Desmos and then you draw it with the transformation explicit, like here, for example. So you draw x squared and in brackets x subtract 2 squared, and you just see straight away what the transformation is. You see that it shifted to the right, a translation of 2, 0. So Desmos is really good for exploring transforming graphs, because they can take graphs and they're either following your instructions or they can come up with their own examples. They can make those substitutions, those transformations of the argument of x, and then see immediately in real time. They can see what happened, what the effect of that is. So I'm assuming that's happened beforehand, so they know that this is going to represent a translation 2 to the right, and this translation 2 to the right and 3 up, and so. Hopefully by this point they are able to say to you, well, look, that's what x squared looks like, and then it's got to go 2 to the right, and so that's what x subtract 2 all squared looks like. And then it's going to go up by 3, so we're going to get something which looks like that. X subtract 2 squared plus 3. And then, of course, we're interested with the third example, what do they do? And I think lots of them will forget what they've just done, and they'll just straight away start trying to factorize it or do sort of something else as well. But of course, what you want to do is go to complete square. It's x subtract 2 squared subtract 3. And so what's going to happen then? It's going to go down by 3. So it's going to be down like that. And so making sure they can translate from a standard graph, so not translate, they can read, I think in the context of the word transform, translates a bad verb. So in the context of the transformation questions, they can take an expression and read it in terms of, read it in relationship to the simple graph they started off with. And then, of course, once I've got going, then of course I can now get carried away. So if I know that in there in the bottom right hand corner in sort of bluey color, if I know that is what that with vertex at 2, -3 and y-intercept at 0, 1, if that's what that one looks like, then what about the others? So what transformation has taken place? If you want to think of this as f of x is x squared subtract 4x plus 1, then what are these? And then what's the transformation? So if you want to share some ideas in the chat or out loud, whichever is easiest for you, don't mind. So if you think of f of x as being x squared subtract 4x plus 1, what are some or all of the other three? In terms of the sort of the function f. Second is negative fx. I agree with that. Okay, that's negative fx. Do we agree with that? Oh, sorry, second bullet point. Sorry, second bullet point. That's negative fx. Yeah, sorry. I was going to say I don't agree with that for the third one, but it wasn't the second one. It was the third one. Yeah. So quite possibly, Gary. It probably helps think of it as terms of functions first, and then we'll come to the transformations. So Eusthathios, you're saying they're both reflections. Johnny, for which one? Sorry, Johnny. So number 3, f of negative x. And Johnny, so f of negative x, but also f of x plus 4. I mean, we can check that algebraically. F of negative, third one, negative f of x. Last one. And then let's come back to this one. So that's intriguing, isn't it? There might be 2 of them. Thank you, Constance. F of 2x. That's what I hoped it was. I just wondered if I'd made a mistake there. That's what I wanted to be, f of 2x. It's 2x all squared, then subtract 4 lots of 2x plus 1. So clearly we've got reflections. For the first one, we've got a reflection in the x-axis. For the second one, for that one, we've got a reflection in the x-axis. For that one, we've got a reflection in the y-axis. And for that one, we've got a stretch scale factor of half parallel to the x-axis. But what's really interesting is, was it Johnny? Yeah, so Johnny suggested something different for the third one. So Johnny suggested a translation. So is that right? Can a translation be the same as a reflection? If I translate my hand, that's not a reflection, that's a translation. So how can a translation be the same because the graph is symmetrical? Thank you, Gary. Thank you, because the graph is symmetrical. And so if I reflect in the y-axis, get -2, -3, and then that point there would have been 5, 1, sorry, 4, 1. And then that point there will be -4, 1. And so if I do reflect the graph in the y-axis, it also looks like I've translated it -4, 0 because it's symmetrical. And now, of course, what's interesting is that I can't tell, because I can't tell whether 4, 1 shifted to 0, 1 or reflected to -4, 1. I can't tell whether 2, -3 shifted to -2, -3, translated to -2, -3, or reflected to -2, -3 because the graph is symmetrical. So that's really nice. There's more than one answer deliberately. And can you get both of them from the students? Can they explain why that's the case? And then, of course, they've got the same thing here, slightly more complicated using the cubic function. So we've got, and also now using a combination of transformations. That was my idea here. So we've got the stretch scale factor a half, and so we've got f of 2x plus 1 and f of -2x plus 1 and something f of something plus 1. And so can we combine the two transformations? Particularly, what's the order? Is it stretch then translate up by 1? Is it translate then stretch? Does it matter? Does it always matter? Does it sometimes matter? Does it never matter? So then the whole start thinking about the combination of or composition of transformations of graphs. And there's a whole thread there to follow through as well. I think the sort of idea of kind of building up from simple graphs to more complex graphs should also include slightly more complicated starting examples, like reciprocals, for example. So, can they sketch the reciprocal graph? Can they shift it by 2 in the y direction? So here's your translation of 0, 2. Here's your translation of -2, 0, then 0, 2. And then we've got a stretch and a translation and a translation. And then the last one. So you've got here this sort of idea of developing complexity. That sort of, if you think about the national curriculum, of increasing complexity over time. So what do we do with the last one? How does the last one follow on from the previous 3? I mean, I hope so. Or have I just cut and pasted the wrong example and stuck it on the slide by mistake? So how might we want our students to use the ideas of the first 3 to answer the last one? I'm not suggesting for one moment they can sketch that function, a linear function over a linear function. That's that's not even on the A-level syllabus any longer. That's a further maths topic. So what might we want them to do? How might they go about doing number 4, sketching number 4, in particular building on from numbers 1 to 3? Any thoughts? Any suggestions, folks? X plus 2 over x. Subtract 2. Probably over.
Oh, I'm sorry. I'm going to talk only because I'm pathetic at typing.
No, lovely to hear somebody else's voice. Yeah, exactly.
I was thinking I would split it as x plus 2 over x plus 2, and
Yes.
then plus the 2x plus 2 over x plus 2, but that doesn't help. Sorry.
No, it does. No, it does. No, it does. Just
idea. 2x plus 4.
Tell me what to do with the 2x plus 2.
2 times x plus 1. So.
Well, no, I think heading in the wrong direction there.
Yes.
What can we do with the 2x plus 2? We could write it again as x plus 2. And then we're going to have
another x, yes.
Another x.
Sorry,
so I've got x plus 2 and x plus 2. And then that last x, I could write as, how can I write that last x? Basically, I really like x plus 2, don't I? So I'm going to write the last x as x plus 2.
Minus 2.
Take away 2. So what have I? Yes, exactly. So Estathos has summarized it for us really nicely. Thank you. So Constance, you're right, Constance. But can you see what Estathos has written and what Sudha has suggested? So now I've got 1, 2, 3 lots of x plus 2 over x plus 2. So I've got 3 wholes. Take away 2 over x plus 2. And so exactly split the fraction. Exactly, Rekha. I can split the fraction. The question is, how do I split it? So I rewrite it as 3 lots of x plus 2 take away 2 over x plus 2, because then that gives me 3 wholes and 2 over x plus 2. It's the idea. Sometimes people call it splitting the numerator. Yeah, it's not dissimilar, Estathos, I agree. This is sometimes called splitting the numerator. And yeah, it's not an A-level technique, but it's a really nice use of algebra. It's a really nice skill to get the students to be able to do, because it really helps them use their algebraic fractions for purpose. Thank you, Sudha. But the idea came from you. I mean, it's absolutely. You said start off with an x plus 2, so you just keep pulling out x plus 2s until you can't, and then you manufacture one more x plus 2, and then we get the 3 wholes. And then of course now we can draw it, because there's my original graph stretched and then reflected and then translated. In terms of functional notation, then, I think it's really good to get students writing these expressions in terms of functional notation, because it gets them used to the idea of composition of functions. I mean, if you think about what lies ahead in year 13, if this whole idea of this is to build up firm foundations for year 13, what's coming down the line in year 13 is the chain rule. And the chain rule really hinges on understanding composition of functions. So getting them to write expressions as composition of functions from an early stage is effort now, which has its reward later. Okay, it's an example of unfinished business. If you kind of skirt around the issue now of writing functions, composition of functions, then that's trouble ahead when you come to the chain rule. So now that's notationally, some people prefer that. F sends x to 6x take away x squared. Don't mind whichever notation that you prefer. Either is fine. So what have we got here? Well, so the first one is obvious. This is f of x plus 2. So there are two functions. There's the function add 2, and then there's the function f of x, 6 times the input, subtract the input squared. And therefore we can see what the transformation is. Any thoughts about those two? In terms of f's? But can we write them as functional expressions and then so I mean, like I was doing earlier, but let's make an explicit task for the students. Suggestions for either of these as expressions using the function, this particular function, the f notation. F of 2x plus 5 is for the third one. I agree with that, yeah. So f of 2x plus 5, because that gives us 12x and the 4x squared. Then we have to add on the 5, and then the second, then the one in the middle is possible might be f of negative x. Let's check that. Does that work? Because then we'd have 6 lots of negative x, which is negative 6x, and then we'd have subtract negative x all squared to subtract x squared. Yeah, so I agree. So those are the three transformations, and then of course we can now draw the graph. And we can just make it a bit harder. We can make it a bit more challenging. So I'll come back to this slide in a moment. My next slide is over to you. So my next slide is what are your questions, either about the practice examples from either of the two sheets. Was there anything from last week you want me to have a look at again? So if you've got some questions, pop them in the chat. If you haven't got some questions, do you want to try those? I'll just kind of sit here for a couple of minutes and see what comes through. So either give me some answers to these, or put some questions in the chat that you want me to go back to from today, or from last week, or from the two sort of warm-up sheets, the two prep sheets that Emma circulated to you. So sort of over to you for any questions, comments, requests. Alternatively, you can have some productive struggle with these. I'm happy to take answers. I'm happy to take questions.
Sorry, can I talk, if that's okay? I'm Sudha.
Yes, yes.
I was looking at your expressions, question 10, where you'd asked for the minimum value obtained in the practice sheets that you'd sent online.
Yes, exactly. Sorry, yes. Question 10, sorry, yes.
So, when I did complete the square for these, and
yeah.
But how can you get I always thought you could plot the equation for an equation. Can you plot an expression? And when you have x and y, how do you evaluate the negative values? So for instance, the first one, x plus 3 the whole squared is what you get, and then you get a y minus 5 the whole squared plus 16 is what you end up with.
Absolutely. Let me. I'm just clearing off my slightly too many speech marks. Why did I put so many of them on one page? How many questions was I expecting? Right. So yes, question 10. So you're absolutely right, and I think from memory that's correct as well. So it was x. Was it x?
Yes, it's x plus 3 the whole squared.
Plus y,
plus y minus 5 the whole squared, and plus 16. That's what you get, yes.
So the minimum value is 16. So the minimum value is 16. Achieved when x is -3 and y is 5. So you need to. So what you've got here is a surface. You've really got z equals. You've got a two-dimensional surface in three-dimensional space. So you've really got a surface with z values, and the lowest the z value can be is 16, and that happens when x is -3 and y is 5.
Got it. Okay, I was looking for an equation and I said, surely you can't find a minimum value for unless you have an equation, and how do you evaluate it for an expression? That makes sense. Thank you.
That's brilliant conversation there, because that's exactly what you want students to say. You want to say, well, it's not, it's an equation. No, it's an expression. And, you know, okay, I didn't say it, but the implication is that x and y can take all possible real values. I agree. I should have said that.
No, not at all. But thank you. That's great.
Values. And what about the second one, part B? I haven't got it in front of me. It was.
I can give that to you. That was x squared minus 2xy without you having to write it. So 2y plus 2y squared plus 8y plus 20. So the way to factorize that was, I mean, the way I did it was x. Yeah, that's right. Yes, yeah. And plus 4.
Plus 4 at the end. Okay, so same idea. We've got a three-dimensional surface. By the way, these look great in GeoGebra. So folks, if you want to know what these look like, start using, so Desmos is really good in 2 dimensions. GeoGebra is really good in 3 dimensions. So you plot this in GeoGebra, and so the same thing, you've got a surface, and you're saying, what's the minimum value? The minimum value of the surface is 4, and it occurs where y equals 4 and x equals y. Oh, okay, so x equals 4.
So, that's right. Okay,
so
that's great.
The minimum point is 4, 4, 4.
Perfect, beautiful. Thank you.
Let me just nip back to the questions. So people carry on with the questions. Thank you. That was great. Thank you. Any more questions from the practice sheets people want to ask me about? Thank you. Constance, you're saying the first one is f of x plus 1. I agree with you. I wonder how did you work it out? Was that just an amazing lucky guess, Constance, or do you have a method? And then f of 4x for the next one. Because, and we can check it, because we get 4x subtract 4, which is indeed therefore 16x, x subtract 1. Constance, I wonder how you did the first one. If you want to share the first one with us. Factorising, lovely. Factorising notice the shift. So it factorises into x plus 1, x subtract 3. And then you think, oh, I see, yes, everything has, so the x has become x plus 1, and the x subtract 4 has become x subtract 3. X subtract 8. From Leah, and by the same argument, noticing that x has become x subtract 8 and x subtract 4 has become x plus 4. Do we agree with that, folks? That would be. I'm going to challenge you on that one, Leah. Sorry, I'm going to check, because that would be x subtract 8, x subtract 12. I would say. So I'm going to challenge you on that one. So I really thank you for suggesting it. And then Constance, you're saying x subtract 4 for that one. Yes. Okay. Yeah. Precisely. So x subtract 4 for that one, and that I do agree with, because x has become x subtract 4, and x subtract 4 has become x subtract 8, and so the question then is about number 3. So number 3 I think is the hard one. Number 3 I think is the hardest one. Okay, but again, I hope you can see the value of that. So getting them used to the idea of composition of functions. I mean, you could even go further. You could say let g of x equal 4x for the second one, and so this function is f of g of x. Or you could say let h of x be x plus 1, then it's f of h of x. So you're getting them used to the idea of thinking in terms of composition of functions, so that when you come to the chain rule down the line, they understand the structure of the chain rule in terms of composition of functions. I said I'd do some fun stuff with circles. I'm not going to go through it in detail. I'm going to just kind of let you. You'll have the slides and you can kind of play around with it. This is one of the questions from the practice sheet. What people think? Question 9. If you did it, what did you decide? Question 9. So you've got the circle x squared plus y squared is 36, and you've got the circle center 6, 8. Radius 4. I wonder what people. So it went for a touch at a point. Okay, that I agree with. So they do touch at a point, and the question is how do we work that out? How do we convince ourselves that's the case? So I agree they touched a point. Though mine appeared not to, but you know, just my pen. I wonder what the reasoning. So sort of you gave me that answer. What was your reasoning for that?
I drew a line from 0, 0 to the point and extended it. So, so it's from 0, 0 to 6, 8. Yes, that's right. And measured a distance of 4 because I knew the radius of this circle, this x squared plus y squared equals 36. And I knew that the radius was 6. And that's how I decided that it would touch. And then I realized all the points around were either above or below. And so it couldn't cut at more than 1 point.
And the crucial fact, which you must have used, and thank you, Gary, thank you, Simon, for the chat, is recognizing that the total distance is 10. So 6, the point 6, 8 is 10 away from the origin. 6, 8, 10 makes a Pythagorean triple, and the 10 is the same as the summers 6 plus 4. So this has got to be 10 to be a right angle triangle, and it is 10 because 6 plus 4 makes 10. So intersecting circles is just a really good activity to explore with your students. So what happens when those two intersect? Well, how do we go about solving them? How do we go about finding where they intersect? Well, the natural thing to do is solve them simultaneously. So let's subtract, say, and so I get negative 2x subtract negative 12x, which is 10x, and then I get negative 8 subtract 20, which is negative 28 is 0. So my x value is 2.8. And my y value is, well, substitute it in, and I'll get my y value, whatever it is. Okay. So what happens? What happens when they intersect? You can see when you substitute it, you're going to get y squared equals. You're going to get y squared is 5.6 and 8, so it's 13.6. Take away 2.8 squared, which is something. And so you're going to get 2 values for y. Okay. So why is that? Pun fully intended, because it looks like that. So you've got 1 x value and you've got the 2 y values, and they're symmetrical because I've chosen the equations of the circles to do that. Okay, so what happens with those two circles? Well, if we do the same thing, subtract them, we're going to get negative 2x subtract negative 16x, which is 14x, and then negative 8 subtract 48 is negative 56 is 0. So x is 4 and y is, well, so we're going to get y squared, and then we're going to get y squared is 2x plus 8 subtract x squared, which is 8 and 8 is 16, which is 0. Oh, okay. So what's happening there is that they are touching. There's only 1 point, x is 4 and y is 0. And then the third case, we're going to get negative 2x subtract negative 20 is 18x, and then negative 8 subtract 84 is negative 92. And so we get x is 92 over 18, which isn't very nice. 46 over 9. So 5 and 1/9, not lovely. Then we work out our y values, and what will happen is you get y squared is less than 0. When you do the arithmetic, you get work out the arithmetic, you get y squared is less than 0. So what's happening? So they're not intersecting. But in the first case, we had x equals 2.8. And that's the common chord. So x equals 2.8 is the common chord. Here at x equals 4, we've got, well, it's sort of the common chord. It's the common tangent. Okay, it's the common tangent to the circles. So what's this? So this is at whatever I said it was, 5 and 1/9. Did I say that? 18 over 92. Yeah. So this is 5 and 1/9. And what's this? It's not the common chord. It's not a chord. It's not the common tangent. It's not a tangent. What is it? It's called the radical axis. It's called the radical axis. And there are loads of lovely things about the radical axis, which I'm not going to go into now. But if you want to explore the radical axis of two circles, there's loads of wonderful geometrical properties about the radical axis. Let me describe one. If you take any point on the radical axis and draw a tangent to either circle, then those tangents will be the same length. Okay. Now it's not because it's symmetrical, and it might look symmetrical, but it's not. I mean, I could do it up here, couldn't I? I could draw that tangent there, and I could draw that tangent there. So those tangents will be the same, well, those tangential segments will be the same length. And that's always true from the radical axis. If you start on the radical axis, you can draw equal length tangents. So it's extending the circle theorem. So the circle theorem from GCSE is that one point to the same circled, this is one point to different circles. And of course, proving why that's true is a lovely piece of algebra, a lovely good bit of productive struggle. But I couldn't talk about graphs without not mentioning that, because of course, think of all the practice of circles, all the practice of coordinate geometry you're going to get by solving these problems. And the last thing I wanted to mention is about altitudes of a triangle. So the altitudes are the heights of a triangle. So the altitude of a triangle is the height from one vertex to the opposite side. So the altitudes are like that, and it looks like they intersect at one point, and they do. They are always concurrent, and they're concurrent at a point called the orthocenter. You will know, and your students may know, about perpendicular bisectors. So the perpendicular bisectors intersect at the circumcenter. Oops, delete my triangle. Perpendicular bisectors intersect at the circumcenter of the triangle. You can draw a circle around the triangle using the circumcenter where the bisectors intersect. That's quite a standard thing at GCSE, but the altitudes are much less well known. And there's an example for you. There's an example for you to play around with or to give your students, and just to work it out, to work out the equations of the three sides, and then the equations of the three altitudes, and then the intersection point of two of the altitudes, and check that the intersection point satisfies the third altitude. And you can just see what good fluency practice that is, with a lovely outcome that you get the fact that they're concurrent. So I think that's really well worth doing. So in conclusion then, we're trying to avoid trouble ahead, e.g. say with the chain rule, and therefore when we introduce functions early in year 12, we really think about composition of functions to set up the chain rule. We're aware of inequalities at GCSE, maybe having been taught very much in terms of they're like equations, but just with a funny sign in the middle. And so we're recasting them in terms of functions to really think about values going in and values going out. And equation is when we get one or a finite number of values out, and the inequality, sorry, if one finite number of values in gives us the value, the output value, and the inequality is when a range, a set of input values gives us a group of an inequality of output values. Tactics and strategies. So the strategy might be that partial factorization method I showed you, if you were not familiar with that, to find the coordinate of the vertex. That had limited generalization, so much more powerful is to think about completing the square, and then think about the implications of that, and moving away from the specific with quadratics, which is it's the number in the bracket, it's the number outside the bracket, with one of them changing their sign, to something much more general about what is the minimum value of the expression inside the bracket, the squared expression, hence what's the expression of its square, and then hence what's the overall minimum value of the expression. I hope you've seen that in these questions there is lots of desirable, difficulty, and productive struggle. In terms of getting the maths from them, well, these are my favourite questions. I've asked you what's the same, what's different quite a few times. What do you notice? But then, of course, and agree or challenge, we use that on the inequality slide. But just generally engaging with the students, well, we want to find where those circles intersect. So what might we do first? What might we do next? Why did we do that? Why didn't we do that? So those questions coming through again and again and again, specifically thinking about that graphs are representations of functions. So really connecting graphs and functions. They're too often seen, I find, by students as they're different chapters, so they're different topics. They're not. They're flip sides of the same coin. Hence, what's the same, what's different about a graph and a function? Part of the answer being the graph is the representation of the function. So that's going to be it from me. Thank you. It'd be really useful to get some feedback from you. So fingers crossed I've covered this correctly. Let me just find the link in which Emma sent me. So that should work for you. That should take you to an evaluation form and a feedback form. Can someone just click on it and check that it works? I'm just wondering about that last backslash, whether that was correct. So that should take your evaluation form. It'd be really fantastic to get some feedback from you, some comments like last time. Please do go and have a chocolate treat. I'm sure since after my starter question, you've been thinking about nothing but dark chocolate bounties and Snickers and such things. Thanks, folks. Thanks for confirming since for the last 2 hours. So please do go and have a treat, but please evaluate before you do so. Unlike last time, I'm not in any hurry. I'm really happy to answer questions about today, about last time, about any of the practice questions, any of the prep questions. I'm at your disposal. I'm sure at least some of you will disappear now. I'm going to have a coffee or whatever. So bye for now. Hang on if you want to. Thank you, folks. Thank you, folks. Thank you for your kind words. Thank you. It's been fun. I've really enjoyed it. So I think I can probably stop the recording. Actually, no, I'll leave the recording going in case there are any questions which come through. Thank you, everyone, for your contributions. Thank you for making suggestions. Thank you, Shashi. I mean, I hope very challenging hasn't put you off. I mean, I wanted to give you lots of things to take away and think about. So I hope challenging is a positive word. Oh, good. Oh, thank you, Shashi. Phew. And clearly you'll get the slides and you'll get the recording, and you'll be able to kind of go over things in your own pace, in a way which suits you best.
Hi again. What I might want to ask is probably not related particularly to this course, but about maths.
Yeah.
I'm an NQT, and I'm going to make a scheme of work for year 13s for mechanics and statistics. Is there any place where I would be able to see some schemes that are already made by someone who knows realistically what is possible to teach in what span of time?
I mean, the first place I would start is anyone who's left in this meeting. So anyone who's still here, do you have a year 13 applied scheme of program study that you could happy to share with our colleague from what school are you from? Sorry,
Kingsley Academy. I can put my email address.
Yeah, so I mean, that's the first thing to do, because that's the whole point about being in a partnership. That's the whole point about being part of a team like this. So if you want to put your email in the chat, and then if anyone has got a scheme which they think works well, that they're happy to share, then please do. That'd be great.
Thank you so very much. That's great.
The other thing I think that's definitely better, because that's been tried and tested by a real person, by real teachers in real classes. I mean,
of course,
I would have thought your exam board, most of the exam boards produce a sample program of study. Whether it's realistic or not, I don't know. It depends what your exam is. Depends a bit more what the students are like. But the first place to start is with each other. Share and share alike. So anyone who's here, who's left, I think. Breda or Constance or Louis or Nick or Paula or Shashi, if you have anything to share about year 13 applied, then please, there's an email there to do so. Right, folks. Any more questions, or is it okay if I start closing the meeting? So Breda and Constance and Nick and Shashi. Thanks, Shashi. Constance, thank you particularly for all your contributions. Thank you for putting lots of answers in the chat. Keep keeping the chat going. Thank you. Okay, I'm probably going to wrap this up in a moment. Nick and Breda and Sudha, if that's all right.
Yes, thank you so very much once again. It was a really great session. I had a good time. Yeah, and I also felt a little inadequate, but in a nice way. Thank you very much.
I didn't want to make you feel that. Sorry.
No, you didn't. You didn't. It just tells me I have to learn more. Thank you.
Thank you. Okay, Constance. Yeah, far away. Do you want to put your mic on? Is that, or are you happy chatting? Don't mind either way. Okay, fine. Yes, so I do use it a lot. I think it's really important. No, completely understand. I completely understand. So yes, I think it's really, really important to use identity. I'm just kind of wondering whether I'm now worrying about today. Did I use it today when I should have done? Yes, use it there. Bit lazy there, perhaps. I used it. Yes, okay. So, just right from the start, I just say, look, this. So, what it means is that whatever you have on the left is automatically the same as what you have on the right. So I just find a blank slide. Where was it? Let me just make a blank slide. So I just make it really clear to the students that it's asserting the equivalence, the identicality of the two expressions. So if I write 2x plus 4 equals 2x plus 2, I'm saying, oh, okay, so I just read a comment in the chat, okay, and then I'm saying that, yeah, I'm saying that's true for a value of x or some values of x. If I write 2x plus 4 is the same as 2 of x plus 2, I'm saying that's true for all possible values of x. I just make it clear that they mean different things. I mean, I just use it all the time. I've just learned to use it. I mean, I'm sort of, I don't really have a response to your comment apart from like phew. At least I was consistent. Like panic over. At least I was consistent. I've just learned to do it. It's just really important to me to do so because these mean different things. This is a claim which may or may not be true. So, is this true? Yes, this is true. I mean, equal sign is really interesting. Some research. I can't remember who did it. Although I give the name. It's going to come back to me. There's some really interesting research about equal signs, which is that if you give children something like that, quite young children, that, what they'll say is they'll say, no, that's wrong. You have to write +1 or 1 plus. So what they're reading is they're reading the equal sign as an instruction to make equal. So they're reading the equal sign as saying make it equal, make 3 equal to 4 by adding 1, and that's not correct. What they should be saying is this is a claim 3 is 4, which is it true? No, it's a false claim. And so 3 equals 4 is an assertion, is a claim, which can be false. It doesn't have to be true. It doesn't have to be made true. And so this is the relationship or the relation of equality, and that's a correct interpretation of the equal sign. What a lot of students think is that it's an instruction to make equal. Yeah, exactly, and very much use it for simplifying expressions. No, precisely. So when I'm saying that x plus 3 all squared take away 2 is the same as x squared plus 6x plus 7, I'm saying that whatever value of x I have on the left hand side and whatever value of x I have on the right hand side, they will always be the same. They will always be true. So yeah, I think it's really powerful to use. So go ahead and do so. Okay. Well, in which case, if that's all right for now, I will bring this to a close. Is that okay, Constance? Breda, are you still here? Or are you a Zoom ghost somewhere in the distance? Ooh, good timing. About to run out of battery. Right. Okay, I'm going to bring this to a close. I'll stop the recording.